Welcome! This is a fifth section of our Hadoop'able problems course. In this section, we'll be looking at the business and point of sale, so we'll be analyzing transactions in the service. So we will write an application that analyzes transactions in a streaming way. We will try to find top seller products and enrich those products with some additional data, and such results will be published to other systems. And this is a first video in which we will be looking at the trending supply chain. So we'll be finding top seller item in a streaming way. So we'll create a streaming job that analyzes transactions. We'll be writing tests for our job and finding top sellers. Let's start from looking at the test. So we have our find top seller job test that extends Spark Streaming Suite. So this is our usual Spark Streaming Suite. We need to have an app name and class that is under test, and this is a find top seller job. We will be going into that logic in a moment. So we have a test that it should find top sellers from a stream of transactions. So we have an input of 5 transactions. First transaction is for item 1, second for item 1 also, and third is for item 1. Then for item 2 and 3. But let's look at the transaction case class. So transaction has an user ID, item ID, and amount for which that transaction was done. And our top seller job needs to find out if within some kind of time window at least 3 transactions for the same item ID happen. If so, then it returns top seller case. So we have an expected output of top seller item 1, some description of our item, and discount. Let's focus on this field. So this is an item ID field, same as here, because there were 3 transactions for item ID 1, so output is only with that one ID. Item 2 and 3 wasn't happening 3 times, so it is not in the top seller. Top seller is a case class that has an ID, this is item ID, description and discount. Next we are creating our queue that will be an input transactions, streaming results to which we will be appending results. We are processing transactions, adding it to streaming results, starting our context, adding input to RDD and find out if the expected matches actual output. But let's go to the job and actual job logic. So as usual, when we are building streaming application, we need to extend Spark Streaming application, give an app name, that is a top seller, do some Spark config, and function that starts processing. So it uses Spark Streaming context and has 2 important methods. First is a dstream provider transactions. So this is our provider that will create a provider that fetch data from Kafka topic. Kafka topic is called transactions, and the serialized transaction to transaction case class from JSON. So we have our transaction, and we also have Kafka sync to which we will be sending top seller items. But the actual logic happens in the process transaction method. So let's look at this method. So we have some kind of documentation here. So it says that top seller is when number of transaction in time window is greater than or equal to 3, or some amount of all transaction is greater than or equal to 100. So we have 2 type of values. So we cannot do a simple reduce, because we could do reduce by key and calculating how many transactions happen, but then we will lose an information about the amount of all transactions within time window. So firstly, we need to define a time window. So we are saying that our time window should have 5 seconds and sliding 1 second. So every 1 second, new time window of 5 seconds will start, and those transactions from that 5-second time window will be analyzed by our logic that is underneath. So firstly, we need to map stream of transactions to pair stream. So we need to create a pair where key is an item ID and value is our transaction. Next, if you want to only calculate, we could do reduce by key and just calculating sum, so adding elements. but we need to have two kinds of informations. First is a count of transactions, and second is sum of all amounts. And we will use a special method that is available in Spark and is very performant. So it is a method combined by key. We could achieve the same thing using group by key, but it will be not very efficient because all values that has the same key will need then be to send to the one executor in Spark. And we don't want to do this because it will be too much data on one executor. But combined by key is doing similar thing, but it sends only the actual result. So for the specific key, it calculates some values and sends those results to the specific executor. Combined by key takes three main arguments. First is a create combiner. So we have a case class that is a top selling aggregate. This will be a result from our reducing function. So it has a count field and sum of amounts. Count will be counter of how many transactions happen within time window, and sum amounts will be sum of all amounts for every transaction in that time window. Create combiner is like initializing our top selling aggregate. So if that function will be called for the first time, we will initialize it to top selling aggregate with counter equal to 1 because it's a first transaction and amount equal to transaction amount. Next step is to merge two values. So we need to merge new transaction after we create top selling aggregate with that top selling aggregate. So we are getting a top selling aggregate count and we are appending 1 because we are calculating occurrences of numbers of transactions, and we are adding a sum of amounts that is already in the top selling aggregate to transaction amount of new transaction. So this is a second phase. And third phase is to merge two top selling aggregates. So this is a merge combiner. So first and second one, top selling aggregate, we need to merge them. So we are just adding from the first transaction top selling aggregate count to second and some amount of first to second. And we are creating yet another top selling aggregate. And we can see that in those methods, everything is immutable and pure function. So we can execute it in a distributed way easily. And Spark is leveraging that fact. Last argument that we are passing here is a hash partitioner with numbers of partitions. If we have 8 executors working, then we can pass here 8 partitions as well.